Hi, show that 50 raised to the power of 3 over 4 times 5 over root 2 raised to the power of a negative half is equal to 10. Try and simplify this. That's my first attempt, is to write this as 50 a quarter. And further to that, we can simplify what's in the brackets here to write this as 25 times 2. Raise this to half, and then we have another half, which is the quarter, and then finally out here we have it cubed. Now we can simplify this in here to give us 5, because the square root of 25 is 5, and we have root 2. So we simplify these inner brackets, and so we have 5 root 2, and then we have 3 times the half. So this now is raised to 3 over 2. Now this, we want it to be a positive index, so we'll just write the inverse of this, which is root 2 over 5 raised to half. Root 2 over 5 raised to a half. That's equivalent. Now we can go ahead and multiply this numerator by this numerator. And remember, this numerator is root of 2, and we're taking the square root of that. And the denominator, well, let's actually write it so you can see where it goes. So we have 5 root 2 to the 3 over 2, and this is times root 2 raised to the half over 5 to the root 2. Now if we multiply here, this, if we break this down, this will be 5 raised to the power of 3 over 2. So we have 5 raised to the power of 3 over 2 times root 2 raised to the power of 3 over 2. And then here we have root 2 to the half. And in the denominator here we have root, or 5 raised to the power of a half. So we have a base here of root 2 and a base here of root 2. So we just have root 2 as our base. We add the indices. 3 over 2 add a half gives us 4 over 2, which is the same as 2. So we have root 2 squared. In fact, let me just write this first. We have 5 raised to the power of 3 over 2 first, and then we have root 2 squared over root 5. Further to this, root 2 squared is the same as 2, and we have this as 5 raised to the power half in the denominator, becomes 5 raised to the power of a negative half. So we have here 5 raised to 3 over 2. We bring this into the numerator as 5 to the minus a half. And then also we have 2 root 2 squared, which is 2. Now we have a common base here of 5, and we add 3 over 2 to minus a half, we have 5 raised to the power of 1, and we have 2, which gives our result of 10. So careful use of indices here. First, we simplified 50 raised to the power of 3 over 4 by looking at 50 and finding the square value here, which is 25. We can simplify this in here, the inner brackets, and then we just have 3 times a half. Again, we simplified here to give us root 2 raised to the power of a half and 5 raised to the power of half in the denominator, or root of 5. Further to that, we simplified here again to have 5 raised to the power of 3 over 2 and root 2 raised to the power of 3 over 2, which combines with this base root 2 raised to the power of half, which you can simplify to root 2 squared, which is root 2 times root 2, which gives us 2. We take root 5, or 5 raised to the power of a half, into the numerator, and it becomes 5 to the minus a half, and that with 5 to the power of 3 over 2 gives us 5 raised to the power of 1, which is 5, and the 2 from root 2 squared, which gives us 2. So we've just shown that this is equal to 10. Thanks for watching. I'm Alistair. Prove that x times x minus 2 is equal to 3 if and only if x is equal to negative 1 or x is equal to 3. In mathematical language, we'll write this as is equal to 3 if and only if, and if we simplify, expand this, clear the brackets and rearrange, we have this as x squared, this whole statement here, it's x squared minus 2x minus 3 is equal to 0. So our statement is x into x minus 2 is equal to 3 if and only if x squared minus 2x minus 3 is equal to 0. And we must carry through our statement, because this double implication, if and only if, applies to each step as we go along. So here we factorize, and we have the two factors, x add 1 and x minus 3 is equal to 0. And that's if and only if x add 1 is equal to 0, or x minus 3 is equal to 0. If and only if x is equal to negative 1, or x is equal to 3. So there we have it. We've shown here, or proved, that this statement is true if and only if x is equal to negative 1 or x is equal to 3. In other words, the solution, two solutions to this equation can only be negative 1 or 3. Thanks for watching. I'm Alistair. Hi there. If n cubed is even, then n is even. Again, we'll use the contrapositive or proof by contraposition. And the contrapositive to this is that we negate both sides of this implication to write that if n is odd, it implies that n cube is also odd. Now if we take n to be 2k add 1 to represent some odd number, then n cube be 2k add 1 cube, which is equal to 2k add 1 squared times 2k add 1. Now 2k add 1 squared would give us 4k squared add 4k add 1, and we multiply that by 2k add 1, and this gives us 8k cubed add 12k squared add 6k add 1, and if we factorize this, we have 4k cubed add 6k squared add 3k add 1. Now this is an integer, and so we've proved that the result n cube is odd if n is odd. So the contrapositive is equivalent to what we've been given here initially, the initial implication. So to negate it, the result is the same. Thanks for watching. I'm Alistair. Hello. If m times n is odd, then both m and n are odd. What I'll use today is something called a contrapositive. And what it means is that we have an implication here. We just negate both ends of the implication and solve that. Sometimes it's a lot easier to do that than to solve it as it is. So the contrapositive of this is if at least one of m and n is even, it implies that m n is even. Note the negation of m, both m and n, is at least one of them. So, and if we have m as 2k and n as equal to another even number, well, in fact, we'll put this as an odd number because at least one of m and n is even. The product mn follows directly from this to give us 2k 2l add 1, which indicates that this number is even because it's multiplied by an even number here. Or further to this, we can have 2 brackets 2kl add k. So if at least one of m and n is even, we have m being even and n being odd. The product mn is shown here to be even. Thanks for watching. I'm Alistair. Show that the sum of two even numbers is even. Let me call these numbers A, which is equal to 2n add 2n1, and B, which is 2n2. So if we add A to B, we have 2n1, 2n2, which we can write as 2 into n1 add n2. Now n1 add n2 is an integer, and we'll call it q. So nq belongs to a set of integers. So since n1 add n2 is an integer, we have the result of adding two even numbers is even, and we've proved that, seeing that q is a member of the set of integers. Thanks for watching. I'm Alistair. Hello. Prove that the product of any three consecutive positive integers is divisible by 6. In my previous video, we looked at the three positive consecutive integers, n add 1, and n add 2. So if you were to look at the product of these three consecutive integers, positive integers, where n belongs to a set of natural numbers. From our first video I published today, at least one of these numbers is divisible by 2. I've shown that for each one of these they're divisible, at least one is divisible by 3. So we have at least one is divisible by 2. So see video 1. And at least one is divisible by 3. At least one is divisible by 3. So since the product is divisible by 2 and 3, since product is divisible by 2 and 3, then it follows that the product is divisible by 6. Don't take my word for it. Select any three consecutive numbers and check for yourself that the product is divisible by 2 and by 3, and also by 6. Thanks for watching. I'm Alistair. Hello. Show that the sum of two odd numbers is even. Let those two numbers be A and B. And the form of these numbers in the form 2n add 1. So if we add A to B, and the forms are 2n1 add 1, it's the first odd number, and then we add it to the second odd number, 2n2 add 1. Now this gives us 2 into n1 add n2 add 1, which we can write as 2p. Now p belongs to a set of integers. So this shows that the sum of two odd numbers is always even to p. Now this is an integer, n1 add n2 add 1. It's an integer, and any integer multiplied by 2 is even. Thanks for watching. I'm Alistair.